Welcome to N19, Vsepr, and 3D geometry of molecules. So Vsepr stands for valence shell electron pair repulsion, which provides us the idea of what's going on with the shape of molecules, basically the structure around a given atom is, excuse me, mostly determined by minimizing electron pair repulsion. So when we were writing our dot structures two-dimensionally, excuse me, I'm sorry, I asked you guys to place your outside atoms as far apart from each other as possible. Well, this model, Vsepr, helps us explain why that is. We want the maximum distance between bonded electrons as well as lone pair electrons, but keep in mind we are focusing on the central atom. So we use this axe method to help us determine the actual shapes. A represents the central atom. So every molecule you're going to draw with dot structures has a singular central atom. Yes, sometimes they can have two atoms in the center. You pick one of them and you define the shape around that one, if that is the case. X represents how many bonded atoms. Now, a single bond, a double bond, a triple bond, they all count as one bonded atom. Doesn't matter how many bonds there are between two atoms, it's still one bonded atom. X represents the number of lone electron pairs on the central atom. So we've been drawing dot structures, and we have lone electron pairs on the outside atoms. Those do not count. Again, we are focusing on lone pairs of electrons on the central atom. And then if we write our axe formula based on a dot structure, we add up X plus E, and this gives us what is known as the steric number. The steric number is going to help us later on in supporting our determination and prediction of hybridization. Questions on this axe method? Okay, so here we have a little chart and lots of forms of the axe formula, again looking at different molecules. Now notice here in the middle column it says the electronic geometry, meaning if we were to assume and just focus on the electrons that are around the central atom, not the bonded atoms, just the electrons, then these shapes would be produced based on the far left axe formulas where there are no lone electrons. AX2, AX3, X4, X5, X6. Those 5 shapes correspond to these electronic geometries that are listed here. The hybridization of A, again our central atom, notice it only kind of works for the first 3. We'll get into hybridization coming up later. The question marks are there for the bottom 2 rows because chemistry has disproven that type of hybridization. So we don't need to worry about it. Same chart, but now showing electronic geometry and the molecular geometry. So anytime you have 2 atoms bonded, AX2, the electronic and the molecular are going to be the same. However, we get to the next row, we can see that I still have 3 things around my central atom, AX3 or AX2E or E1. It's still 3 things. But because there's a lone pair of electrons, it's no longer a molecular geometry of trigonal planar. It's going to be a bent structure. And we can see that later on. And so forth. So again, I took the time to color code what everything is kind of representing, notice that the electronic geometry differs from the molecular geometry only when you have lone pairs. So if I have no lone pairs on my dot structure on the central atom, the electronic and molecular geometries will be the same. Questions on this? Okay. So going back to this whole electron valence shell electron pair repulsion, we know that these electron groups that are highlighted here, they are bonding electrons. They repel each other. They want to get as far from each other as they can. So in this scenario, we have a trigonal planar structure. The three silver atoms form a triangle at 120 degrees. Therefore, it's the farthest apart. That can happen based on this makeup of your molecule. So going through a little bit, here's linear geometry, 180 degrees. Yes, you need to be aware of the angles. Trigonal planar, again, 120 degree angle, as we just kind of saw. Here's tetrahedral, 109.5. AX4, again, 4 bonded atoms around the central atom. Here's AX5. We have a 90 degree angle. We also have a 120 degree angle. So 2 angles involved with the trigonal bipyramidal shape. And lastly, excuse me, we have octahedral, 90 degrees around everything. There are 6 bonded atoms to my central atom. So these shapes that I have just shown you correspond to the electronic geometry always, but they also refer to the molecular geometry because there are no lone pairs. Again, you start adding lone pairs, the shape is going to change based on that chart we saw earlier. Another kind of view of octahedral in its geometry. Another way of looking at it, I guess. So the effect of lone pairs, and this is where Vsepr plays a role, is what's going on. So a lone pair of electrons actually occupies more space than a bonded pair. If they take up more space, there's going to be more repulsion with a lone pair. Because of this more space, it's going to affect bond angles. It's going to change the shape. Going back again to that chart of electronic and molecular geometries, you start adding 1 lone pair, 2 lone pair, 3 lone pair. The shape is going to change. Bond angles actually get smaller. Atoms get kind of pushed out of the way. No, they're not removed at all. They just have to find a different angle and a different shape to minimize all of the repulsion that is occurring between both lone pair electrons as well as bonded electrons. So if we want to compare the size of the repulsive force, we can look at it in the following way. A bonding pair is going to repel a bonding pair in the lowest repulsive, with the lowest repulsive force. If I take a lone pair next to a bonding pair, it's going to be the next highest repulsive force. And obviously, if you have multiple lone pairs that are near each other, that's going to be the highest type of repulsive force that can change the shape of a structure. Questions on this? Okay. So, for example, if we take ammonia, NH3, on the left-hand side, electronically, it is a tetrahedral shape, 109.5. But from a molecular geometry, the actual geometry, that lone pair on the top of ammonia takes up more space. It's going to repel or have a repulsive force with all of the bonded hydrogen-nitrogen bonds below it. So it kind of forces the hydrogens together, which changes the bond angle, as you can see, down to 107, sometimes 107.5. So, and it gives us a shape of trigonal pyramidal. You can kind of see a little mini pyramid, three-sided pyramid between the N's and the H's, which gives us that trigonal pyramidal shape. Questions on this one? Okay. Same idea. Left-hand side, there are 4 things around the oxygen. It should have a tetrahedral geometry, which it does electronically. But when we actually look at the geometry of water, it has 2 lone pairs and 2 hydrogen atoms bonded. Those 2 lone pairs really repel each other. On top of, they also really repel the bonded hydrogens. So it makes that bond between the hydrogen atoms even smaller, 104.5. So we can see how these lone pairs do affect the molecular geometry, but electronically, ammonia and water, here's ammonia, back to water, electronically they are identical. They have 4 electron pairs around that central atom. In this case, 2 are bonded, 2 are lone pairs. Questions? Okay. All right, so hybridization. Ultimately, it's just the blending of orbitals. And hybridization occurs in order to help minimize the repulsion that occurs between lone pairs and bonded pairs of electrons. So an example, a poodle and a Labrador give you a Labradoodle. Our point here, what we're going to do is we're going to blend our bonding orbitals, which are s orbitals and p orbitals. Remember, those are valence. D, as in dog, orbitals do not participate in this hybridization. They have been disproven. The question marks from earlier of today used to include d orbitals in the hybridization, but no longer. We're kind of still in limbo waiting to find out what chemistry is going to come up with. So from our perspective of orbitals, we're going to take a spherical s, we're going to take a p orbital, we're going to hybridize them so they look like the left-hand bottom of the diagram. It's similar to p, but has some differences. Now, p orbitals by themselves, in the red, we know that one exists on the x, the y, and the z axis. They're stuck there. That's where their mathematical equation says they are. But we've seen that there are other angles than 90 degrees. We've seen 120, we've seen 180, we have seen 90 degrees as well. We've seen 107, we've seen 104. So all those other angles that we've come across can really only occur due to hybridization, because normal unhybridized p orbitals can't move. Questions on this idea? Okay, so an sp hybrid, it's literally called sp because it's made of one s orbital and one p orbitals. Remember, there are 3 separate p orbitals. In this case, 2 of them are left alone and they are unhybridized. So kind of one way of looking at it, the bottom diagram, we're taking that nice blue circle, which is an S. We're going to take one of the p orbitals above it, and we're going to get 2 hybrid orbitals right here. 1s plus 1p equals 2. 2 hybrid orbitals, and then 2 of the p orbitals not hybridized. Questions on this? Okay. Now our sp2 hybrid, as the name suggests, 1s and 2 of the p orbitals are hybridized together. Well, 1 plus 2 is 3. Therefore, my hybrid orbitals have to be 3 separate hybrid orbitals, as we can see here, that are made of 1s and 2 p orbitals. leaving one of my p orbitals unhybridized right here. And then finally, our third type of hybrid orbital, we only have three, is sp3. Put them all together, and we get 4, 1s plus 3 p's, 1 plus 3 equals 4, 4 hybrid orbitals. Now, next thing to note, energy. The arrows, the big black arrows, show an increase in energy from bottom going up. Notice that the hybrid orbitals are right kind of in between an s and a p by itself. So, meaning a hybrid orbital has more energy than an s, but it has less energy than a p. And that's kind of an important aspect to note because, again, energy is the name of the game in chemistry. It's the currency. So by combining these two, they kind of, I don't want to say average, but I'll say average their energy, for lack of a better term, based on these hybrid orbitals being created. Questions on hybrid orbitals? Okay. Well, the last little thing to discuss is how do we get from the steric number, as I brought up earlier, to the hybridization? Well, the steric number is x plus e. So on the couple examples we saw, let's take ammonia, NH3. Ammonia has 4 things around it. So x plus e equals 4. Here on the screen, excuse me, S plus 3 P's equals 4. The steric number is the hybridization. If the steric number is 4, the hybridization has to be sp3. Back up for a second. If the steric number is 3, so AX3 or AX2E1, S plus 2 P's equals 3. So a steric number of 3 will always have a hybridization of sp2, and so forth. Questions on steric number and its relationship to hybrid orbitals? All right, thank you.